All right, guys, we are here to work through the review of the integration and improper integrals chapter. So I was looking through this and I was trying to decide which ones to do, and to be honest, we did really a lot of them today. Today's Tuesday, by the way. So I'm not going to go through as many as maybe I thought, but again, like I said, if you come across something you have a question on or something you need to see or you need to have explained, please let me know before next Wednesday and I'd be happy to go over it. So the formulas page, that's the first one. So I want you to double check and make sure you're looking at the answer key to the review sheet, because it gives you the formulas for integration by parts and then the Lie8, integration of partial fractions, how to separate it, long divide if the top exponent is equal or higher than the bottom, so you're going to have to do that first. Then you've got your improper ones, the ones that have the infinity going on, whether it's in the A position or the B position with infinity, and then of course negative infinity to positive infinity, and then where your discontinuities are. Don't forget that there could be a discontinuity in between. You are going to want to make sure that you remember your inverse trig functions and your integrations there. We've got tan inverse, sine inverse, and secant inverse. Make sure you know them if they've got the A's as well. This is from not last unit with area and volume, but the unit before. So these just might pop on up, and there is one or two in the review. Okay? All right, so taking a look at these, I was really thinking that I would start with number 6. Number 6, we're looking at the integration of x squared plus 2x minus 5 over the x plus 2 dx. Now again, remember, when you're doing long division and you're coming across something and the numerator is higher than the denominator, you have to make sure that you long divide. Because what you need to do is rewrite this fraction as something different. You need to separate it a little bit so that your numerator is not larger than your denominator. So it's, what does it take to multiply x to become an x squared? That'll be an x. Multiply both pieces. And then don't forget to change your signs. So when you change your signs, your first term cancels out. In this case, your second term cancels out, and you're left with negative 5. Well, and you could do a plus a negative 5, or or you can just say minus a 5 over the x plus 2. So what happens is this fraction becomes an x, minus a 5 over x plus 2 dx. So that's what you're integrating. And now this is easy. We didn't even need to do integration by parts here, or partial fractions, I should say, because you already know how to integrate. It's already separated. So you integrate this one, it's x squared over 2, and then this one would be the minus 5 ln of x plus 2, and then you've got your plus c. So that finishes off number 6. All right, the next one I put on my list to do. So I did want to kind of mention numbers 11, 12, and 13. 11, 12, and 13, 11 and 12 aren't so bad. You can kind of take a look at those. Number 11, I did L'Hopital's rule, so I did the derivative of the top and the derivative of the bottom. That's how I got the answer to be 1. For number 12, I broke it apart. So I broke x squared in the denominator apart. So I made it sine x over x, and then a 1 over x, because sine x times 1 is sine x, and x times x is x squared. So I separated it. Now the limit as x approaches 0 of sine x over x is going to equal 1. How did I do that? I used L'Hopital's rule. Now this would be something that I would have memorized, but if you use L'Hopital's rule, you know that it's equal to 1 because the derivative of sine x is cosine x, the derivative of x is 1, and cosine of 0 is equal to 1. So it'd be 1 over 1. So this is something that you can either memorize or do L'Hopital's rule with. This one, if you're plugging in a 0 in the denominator, you do get 0, right? Except for the fact that 0 in the denominator is undefined. But notice that we're coming from the right-hand side. So you need to determine if you're doing a positive or negative infinity. So if you're coming from the right So you've got 0 coming from the right. So you're plugging in like a 0.0001. Well, it's a positive number. And if you keep flip that, that's like 1,000, 1 million, 1 trillion. It's going to positive infinity. So a 1 times a positive infinity is a positive infinity. Now number 13 is extremely confusing. We're not going to spend our time working on it, and you're not going to have to worry about it. I put a little star there and I said go to the end of the review. At the end of the review, you can find the answer to number 13. The next one I thought I would look at is number 16, the integration from 1 to infinity of cosine x dx. Okay? Now, my infinity sign is in the b position. So I'm going to write the limit as b approaches infinity of the integration from 1 to b of cosine x dx. Now remember and make sure that you're writing down all the things you need to for this test. You need to write down all these pieces. Now remember, we need to integrate that. Well, we don't need u substitution to integrate that. We can just go ahead and integrate it. The integration of cosine is sine x, and we want to evaluate that from 1 to b. So that's the limit as b approaches infinity of sine of b minus sine of 1. Okay? Now, the reason I did this one is because when you plug an infinity in here, that's kind of weird and we haven't looked at that. But a sine function looks like this. So it starts at 0 and it goes up and then it goes down and then it goes up and then it goes down. And it's going to be a wave. So the idea is as x approaches infinity, sine really doesn't do any kind of approaching. It goes up and down and up and down. It's oscillating is what that's called. So this one really does not exist. Okay? So since it doesn't exist, I don't care about the rest of this stuff. I just say that this is divergent. Okay? Divergent means that I can't find a sum. This is saying find the sum. Well, I can't find a sum because I cannot do sine to infinity. Okay? So I wanted to do 16 so I could explain that piece of it. All right, the next thing I wanted to look at is number 18. 0 to 4 of 4 minus x raised to the negative 2/3 dx. Now, it's easy to notice, or not notice, I guess, that this is where you're discontinuous. Because if you put this to the bottom like it's supposed to be, let me get more ink or lead, 1 over 4 minus x to the 2/3, you can't have a 4 in x. If you put a 4 in x, it makes this thing discontinuous. So this is where your problem is. Now, if we're looking from 0 to 4, you're going to approach 4 from the left-hand side. So we know that this is going to be the limit as k approaches 4 from the left of the integration from 0 to k of 4 minus x to the negative 2/3. Now, you do have a u substitution here. It's 4 minus x, so du dx is equal to negative 1. So you're just going to have that extra negative thing there. So u to the negative 2/3 du over negative 1. So let's see, we have a negative u. If we add 1 to that, that's going to be a positive 1/3, and then we need to multiply by 3. So we'll end up getting that negative 3 in front. So it's the limit as k approaches 4 from the left, okay, of negative 3 u to the 1/3. And we're evaluating that from 0 to k. So the limit is k approaches 4 from the left of negative 3, 4 minus k to the 1/3, minus a negative 3 times 4 minus 0 to the 1/3. So basically 4 to the 1/3. Okay? Now, when you plug in a 4 here, you get 0. So this whole thing goes to 0. It's approaching 0. Now, for this one, we got to figure out the value of it. Well, a negative negative is a positive 3, and then we're just going to leave it 4 to the 1/3. Now, of course, you know, that's the cube root of 4, but we don't know the cube root of 4, so we're just going to leave it looking like this. Okay. So that's number 18. Now, looking through all these are great problems, And it's not that I don't want to go over them or I don't think they're important. It's just that today in class we spent about an hour doing a lot of these. So I didn't want to waste your time by doing them again. So I just picked a few. So the next one I decided that I would go over is number 25, because we haven't done one like number 25. Number 25 is kind of putting two things together. It's putting in an integration by partial fractions along with this infinity improper integral thing. So we need to put them both together. So this is in the A position. So we have the limit as A approaches negative infinity of the integration from A to 0 of 1 over x minus 2 times x minus 1 dx. Okay? Now, I'm going to do this integration part. Okay? Whoops. I gotta make sure you can see it. So to integrate this, I have to do my integration by partial fractions. That's a minus 2. So that's A over x minus 2 plus B over x minus 1. So I get 1 equals A times x minus 1 plus B times x minus 2. If I make x equal to 1, I get 1 is equal to, that would be a 0, and this would be a negative B. So I get negative 1 is equal to B. Now, if I make x equal to 2, I get 1 equals, if I plug in a 2 here, I get 1a. Plug in a 2 here, I get 0. So 1 is equal to a. So I'm actually integrating 1 over x minus 2 plus a negative 1 over an x minus 1. So I get the ln of x minus 2 minus the ln of x minus 1. Okay? Because this minus is going to make that plus become a minus. So what I can do now is I can rewrite this limit thing. The limit as a approaches negative infinity of this ln of x minus 2 minus the ln of x minus 1. And I want to evaluate that from a to 0. So it just meant that your integration was a little bit longer. Your integration was integration by partial fractions. Okay, so while we haven't done one specifically like this, we've done problems where a is going to negative infinity, and we've done problems where we have to integrate by partial fractions. So we're just putting those two together. So we get the limit as a approaches negative infinity of ln. If I plug in a 0, I get the absolute value of negative 2 minus the absolute value of negative 1. And then if I plug in the a, I get the ln of a minus 2, and I'm going to run out of space, aren't I? Great. Here, I'll just move it down here so we can see it. So the limit as a approaches infinity of ln of negative 2 minus the ln of negative 1 minus the ln of a minus 2 minus the ln of a minus 1. So, this is just ln of 2. ln of 1 is equal to 0. Okay? If I plug infinity in here, ln of infinity is going to infinity. Hold on. We got a little deal here. Because I put the answer to be ln of 2 minus the ln of this is also going to infinity. I think what happens here, there's some indeterminate values, but essentially these two things are going to cancel each other out. And when they cancel each other out, you're going to end up with the answer being ln of 2. Because this is going in the positive direction, this one's going in the positive direction, but when you subtract the two of them, they cancel each other out, and you're left with just ln 2. this one is a tricky one, and it's tricky to know, and I would even argue that in some cases, people would say this is indeterminate, and your answer would be divergent, and because you can't subtract infinity from ln2. You also can't add infinity and subtract infinity and say that that's equal to 0. So with this kind of argument here, when you get your answer, depending on where you're looking and depending on who you're using, your answer might in fact be divergent. Okay, I can take a look in Desmos to see what it says there, but ln2 is how I got the answer. But ultimately, I wanted you to look at the partial fractions portion and how we're going through this. Now remember, this final answer is only worth 1 point. All of this other stuff is worth your approximately 4 points or more. Okay, number 28 was the next problem I wanted to go over, and I think that was the last one I wanted to do with you guys. So 28, we were doing the integration from -2 to 2 of 1 over x plus 1 cubed dx. And the problem is you're discontinuous at x equals -1. Okay? So you have to break this up into -2 to -1 over 1 over x plus 1 cubed dx. And then you have to do from -1 to 2 of 1 over x plus 1 cubed dx. Okay? So when you're doing this first one, this, like if we're looking at a number line, we got -2, -1, and then we have a +2. You're approaching this first one from the left-hand side, okay? You're coming from the left to approach that -1. So you've got the limit as k approaches -1 from the left of the integration from -2 to k of x plus 1 to the -3 dx. Notice I'm getting it ready to take the integration, okay? So when I integrate that, when I integrate x plus 1 to the -3, I end up with x plus 1 raised to the -2 over -2. So I can write that as 1 over -2 to the x plus 1 squared, evaluated from -2 to k. So I get the limit as k approaches -1 from the left of 1 over -2 k plus 1 squared minus 1 over -2 times -2 plus 1 quantity squared. Okay? Now, this one's our one we were looking at first. You can't just plug in a 1 and get a 0 down here. Remember, we can't get 0 in the denominators. 0 in the denominators means this thing's either going to positive or negative infinity. Okay? We need to know which one because we need to be able to say which one this equals. Well, how do you do that? Well, you say, okay, I'm approaching -1 from the left-hand side. Okay? If I'm approaching -1 from the left-hand side, I'm plugging in, let's see, I'm plugging in a negative, so like here's -2, so I don't know, I'm just having trouble here with this. I don't know why. I'm sorry, I was distracted there for a minute. So this one would be -0.9999999. So this is a -1.0000001. Okay? So if you did that, you would have 1 over -2 times -1.00001 plus 1 squared. Okay, well that's a 1 over a negative and then a -0.0000001 squared. Okay, well, if you square it, it becomes positive. This is still a negative 2, but this now becomes a positive, you know, really big fraction, 0.00000000001. Okay? Well, that's just a really big fraction, 1 over negative 2 times, like, I don't know, 1 over 100,000 or 1 million or something like that. Keep, change, flip. You're going to get a really big number divided by a negative 2, but again, it's going to negative infinity, I guess is my point. My point is, because you're squaring this thing, it's becoming positive, but this negative 2 is still there. So we don't care what this is. This thing is going to negative infinity, and it's divergent. Now, if it were multiple choice and they were just asking you for divergent, you wouldn't necessarily need to figure out whether this is positive or negative infinity. If you're doing a free response question, they are going to want to see this negative infinity in order to then get this divergent answer. Okay? So, I hope this helps a little bit. Again, you know, 20-minute video for review I think is way more doable than, you know, if I had done this whole review, it would have taken forever. But if you have any other questions, if there are problems I didn't go over, other than number 13, because we don't need to waste our time on number 13, I'd be happy to show you. I'll either make another video or I can do it in class, depending on the timing of things. Okay? I hope you guys all have a wonderful day, and I will talk to you later.